Hi, I'm Jules Reichenbusch. Welcome to my Instructable on how to build some pretty awesome video lights, starting with this, a baking pan. A baking pan turns out to be made out of aluminum, which makes it really good for heat dissipation, and it's very easy to drill a bunch of holes into it. I ended up mounting 12 10-watt LED emitters on here, and it puts out about the equivalent light output of about a 500 or 600 watt halogen light, drawing about 80 to 100 watts of power. Worked out really well. So my first take on the project, I started with my baking pan, and I got a bunch of LED strips, mounted them on the baking pan, giving me this. Turned out not to be as bright as I wanted, and I also I wanted to use cool white and warm white LEDs to allow me to do color mixing and get a little bit better color rendering index. And with all the jumpers needed on this, it just turned out to be a real pain of a project. And as you might notice, there's a couple quality issues in here, and I had to jumper some wires and sort some stuff out. So I went back to the drawing board and came up with the one that I'm using right now with the 10-watt emitters in it. So with those warm white and cool white LEDs, all you need to do is set your camera to fluorescent, which I'm doing right now because you get a color temperature of about 5,000 degrees Kelvin. I highly recommend you go on Wikipedia, check out CRI, color rendering index, color temperature, lumens, lux, get some background information on this, and you'll learn a lot. So, are we ready to go and ready to build some awesome video lights? Get a little theory first? Here we go!
Let's see how all these LEDs work. These are called 10-watt emitters, but there's actually 9 LEDs internally, all mounted to one substrate. They're all wired 3 in series, and then those 3 in series are wired in parallel. So here's one of our 10-watt LEDs with a current slowly turned up. At first you can see one LED comes on, then 2 others in a different string. This is all with just like 1 or 2 milliamps of current. As voltage goes up to about 8.5, current jumps to 500 milliamps, which is the limit for my power supply, and all the LEDs are on. Interestingly, this gives us just over 2 volts across each LED. To work well and be stable, LEDs need to be supplied with a constant current. I decided to use half warm white and half cool white. Here's the spectrum of a typical LED. Now with overlaying the cool white, and you can see the peak is in the blue. Add in the warm white and it evens out a bit. No light is completely flat. The sun is best, but even that is not flat. Here's a comparison of several light sources including the sun. Notice the compact fluorescent one. That one is really bad with 3 spikes of light at different wavelengths. Okay, let's move on to the current controller for the project. I am using a MOSFET current limiter. This super simple circuit has an NPN transistor with a current sensing resistor across the base emitter junction. Typically, the transistor when conducting has a voltage drop across the base emitter junction of about 0.6 to 0.7 volts DC. The transistor collector is tied to the gate of the MOSFET. As the MOSFET starts conducting, we will reach a point where the current through it, which also flows through the sensing resistor, causes the sensing resistor voltage to go up. As the voltage goes up, the transistor conducts more, lowering the voltage across the gate of the MOSFET. When the voltage across the sensing resistor reaches normal conducting base emitter voltage, the current through the MOSFET stabilizes and remains constant. For pulse width modulation control, I am using the classic 555 timer set up as a variable pulse width modulation controller using a single potentiometer. With the timing capacitor I picked of 470 picofarads, we have a pulse width modulation frequency of 27 kHz. This is high enough to eliminate any flickering. To power the 555 timer circuit, we're using a 7812 voltage regulator supplied by the main DC supply. With the way I have the strings wired 3 in series, we need at least 30 volts DC to supply the LEDs, plus a few volts above that for the MOSFET circuit to work correctly. I determined 34 volts DC as optimum. We will set the voltage during the build. If you want to simplify this project, you can just use an on-off switch in place of the pulse width modulation controller, and I'll show you how to do that at the end of the video. I built this whole thing as separate little modules that will all mount to the baking pan. The additional hardware we will need are a mount to attach the baking pan to the light stand, some support brackets, and a bunch of 440 screws to mount the LEDs and associated circuitry to the baking pan. I used barbecue grill paint. Not that the lights get above 50 degrees C, it just seemed like the right thing to do. Okay, so go to A-Smart or your equivalent and get 3 baking pans. You can order them online if you can't find local ones. Now we need to measure and mark all the holes that we're going to drill. I created a drilling template for this after planning out how many holes were needed and of what size. This is one project where the exact placement isn't super critical. The actual LED mounting holes need the most accuracy, and we will see how to get that. We're going to mark the center of the 12 LED modules by evenly splitting the baking sheet up. Remember, to evenly place 4 across, you need to divide by 5. You have 5 spaces. The same for the 3 down. You need to measure and divide by 4. Hey, it's all math. Life is math. We need holes for the brightness adjustment potentiometer, the on-off switch, the 2 current regulators, the 12-volt regulator, and then the strain relief that holds the DC power cable coming into the back. After marking the location of the LEDs, we need to mark the actual screw hole locations. We're going to hold these down with 440 screws that will clamp down on the edges of the LED plate using the 2 cutouts in each corner. To mark these, hold the LED down, centered on the mark you previously made, and then mark the 2 corners with a Sharpie. Make sure the LED doesn't move between the markings. This is a pain to do when you're trying to film yourself doing it. Once these are all marked, I used a center punch to accurately mark all the holes. The mark gives the drill bit a place to start without shifting. For drilling in metal, this really helps. After center punching everything, it is time to bust out the drill press and start making holes. Use an 1/8 inch drill bit and drill everything. For the larger holes, this will act as a pilot hole. And now it's time for a drilling montage. After all the holes on the bottom of the pan are drilled, we need to drill the larger ones. The mini toggle switch gets a 1/4 inch hole, the potentiometer a 5/16 inch hole, and the strain relief a 1/2 inch hole. For the support braces, we will use 2 per light head to add strength to the baking pan. I drilled a 1/4 inch hole centered on the baking pan where the light stand mount will go, and then attached one of the brackets with a 440 bolt. This lets me use the bracket as a drill template to drill the other hole for the second bolt. That way the holes actually line up correctly. My video shows me marking it, but I actually drilled it with a bracket attached. Once the holes are all drilled, you may have noticed the edges of the holes are rough and have burrs on them. We need to clean these up and deburr the holes. There is a great tool for this, creatively called a deburring tool. You can get them at Harbor Freight and other places. To use the tool, place it in the hole and twist it back and forth until the burr is gone. I noticed that the drilling pushed the metal in a bit around the holes. We really want it flat where the LEDs mount, so this gives us a chance to use a little force and even things out. As you work, rub your fingers across the holes to feel when all the burrs are gone. After the holes are cleaned up, I did a quick sanding with 400 grit sandpaper as a final cleanup and to roughen the bottom of the plate for the paint. Prior to painting, I wiped the pan down with isopropyl alcohol to get rid of any grease and dust. Now let's paint the pans with our trusty high temperature grill paint. Time for the painting montage! Let the paint dry overnight and then proceed to assembly of the light heads. Now it's time to build our current regulators. These lend themselves to point-to-point wiring and kind of floating all the components off of the MOSFET. Start by bending up the leads on the outside. These are the gate and source leads. Then make a small loop in the center lead. This is the drain lead and where we will connect the LED strings. Now take the NPN transistor and flip it so the flat side is facing down. The emitter lead is now on the right. Bend the emitter lead to the side. This will connect to our sensing resistor and ground. Spread the other 2 leads a bit and make small loops in the end of the leads. These will attach to the MOSFET leads we bent earlier. Carefully place the transistor on the MOSFET face down with the 2 transistor leads connecting to the MOSFET leads. We're connecting the collector to the gate and the base to the source. Now we connect the current sensing resistor. As the current goes through the resistor is potentially up to 2 amps, we need to make sure it is rated for the heat produced, or commonly called I²R losses. In this case, 2 amps squared, or 4 times 0.33 is about 1.3 watts. I picked a 3 watt rated resistor, giving us plenty of thermal headroom. Form the lead so that one side can go to the base source junction. The other end will have the emitter connected to it, and then finally connect to ground when we will wire the whole system together. The final component to connect here is our 10K resistor from the collector that will go to the 555 timer pin 3. Come on, little resistor, hold still while I solder you. Now we need to make the 12 volt regulator module. This one's pretty easy. We have a 7812 which has 3 leads, input, ground, and output. But to work well, we need to add a couple filter capacitors. On the input, we're using a 10 microfarad little electrolytic, and on the output, a 0.1 microfarad poly cap. See the datasheet for specifics. Without these capacitors, the regulator can oscillate, causing all sorts of mayhem. These get soldered on so they float off the 3 leads of the regulator IC. Note the mounting tab of the 7812 is the ground lead. So by connecting this directly to the baking pan, we ground the baking pan, which is probably a good thing. Next step is to mount the LEDs using our trusty 440 screws. I cleaned the inside of the pan with 99% isopropyl, eliminating the drill marks and getting the surface as clean as possible before the LED is attached. Each LED has a mark for positive and negative. We want all the positive markings to face towards the mounting point or bottom of the pan. They mount by bringing in 2 screws from the back. Hold them with your fingers on one hand while you place the LED with the other. Then kind of balance the whole thing and attach a nut to one of the screws, and then put the next nut on. It gets easier as you go. When you have all 12 LEDs mounted, double check the polarity. They will not light up if they were reversed. Now let's wire everything up, starting with all the LEDs. I used 18 gauge wire to connect those and had a couple colors on hand. I'm a huge fan of type EE Teflon insulated wire, which is what I'm using here. For the positive DC line, I use red. Tin the connections at the bottom row of LEDs. We will need to tin all of these, by the way, so feel free to do this all in one step. Solder the first wire to the last LED on the left and work across to connect all 4 strings. Then cut pieces of wire to connect the 4 strings of LEDs in series. I used orange wire for this. You will need 8 short pieces. I lined the wire up, gave a bit extra, and then cut. Now it's time for the solder montage. After the strings are connected, we need to connect the 2 warm white strings together and the 2 cold white strings together. Those will both share a MOSFET current controller. One for warm white, one for cold white. Let's mount the pulse width modulation controller and its associated potentiometer. I built the bulk of the circuit on a little perf board. Note the hole for mounting later. This uses standard point-to-point wiring. Instead of mounting the diodes to the board, I mounted them directly on the potentiometer. This is pretty easy. Just make sure the two diodes are pointing in opposite directions, twist the leads on one end together, and then solder. The other ends will go to the pot leads on the outside. Now all we need are two wires to connect the circuit board. If the control works backwards, all you need to do is swap the wires on the pot wiper and the diode junction. Before mounting the circuit board, I made all the connections. I ran a 22 gauge red and green wire for the 12 volts, and then I connected pin 3, which is the output of the 555, to the 10K resistors on the current controller. One 555 timer can run at least 10 of these MOSFET current controllers. The power switch will switch the incoming 34 volts DC to the 12 volt regulator. As the MOSFETs are very high impedance when turned off, we can do this. Wire the two ground connections on the MOSFET together and then connect that to the 7812 regulator ground pin. The 555 pulse width modulation board power leads will connect straight to the 7812 regulator plus 12 and ground. After wiring all the internal wiring, we need to bring in the power cable for the light head. Bring in enough wire through the 1/2 inch hole to estimate what is needed to connect to the ground on the current regulators and positive to the LEDs. Carefully strip back the outer insulation. I used a single edge razor blade for this, bending the wire so that the blade doesn't have to go fully through the insulation. Then split the remaining insulation to help remove it. You probably don't want to do what I'm doing here. I did picture myself cutting my hand wide open while filming. Lay the wire flat on a table. You don't have to cut all the way through, just enough to give it tearability. Much safer than cutting an avocado. Before soldering, we need to attach the strain relief. This is one of those, I'm not quite sure how I'm going to do this in my project design. Initially, I thought of using a connector on the baking pan, and I didn't like the idea. Then I did some research and I found the strain relief on DigiKey that works with the wire that I'm using and mounts into a 1/2 inch hole. Happy day for me. Although getting it to go in the hole is fun. Squeeze that puppy, but don't damage it. Let's connect the power leads. Note, I am using the IEC NFPA convention for power color codes here. See Wikipedia again. Search for Global Wire Color Code. Black is hot and white is neutral, just like your house wiring. Yes, I know the neutral should be light blue, not white, but hey, I'm an American. The other end of the wire will go to a Neutrik speak-on connector. These make great power connections. They are rated for 40 amps and will lock in place. The one we're using has 4 connections labeled 1 plus, 1 minus, 2 plus, and 2 minus. We're using just the one connection, black to plus and white to minus. Yes, I know that sounds wrong, but this is power wiring, not internal DC. Follow the code, my friend. Follow the code. Last step in the light head build is to mount the light head adapter. The mount I bought has 2 of these. One is male, one is female. The female one will mount to a 1/4-20 machine screw. The male one, like me, is a little short. We'll need a 1/4-20 standoff or an adapter. So I went to my local Lowe's store and they were out. So I went to the orange one. and it took me a bit to find them. Lowe's and Home Depot keep these in different locations. Get yourself a few of these. They're great for adapting tripod, GoPro clamps, and anything else with a 1/4-20 bolt on it. To power the light, I'm using off-the-shelf DC switching supplies mounted into a case. Before mounting the power supply in the case, we need to adjust it to 34 volts DC. All of these supplies have a trimmer adjustment somewhere on them. The hard part's finding it. The case I'm using came from Lowe's. I am certain Home Depot sells them also. We're going to mount the power supplies in it, then mount the 4 speak-on connectors and an IEC power jack. I cut pieces of 18 gauge wire, red and black for the low voltage DC, and soldered those to the panel mount speak-on connector. Those are also labeled 1 and 2, plus and minus. Red to 1 plus and black to 1 minus. The other end will have spade lugs crimped onto them. My supplies have 2 connections for the DC output, which makes connecting the spade lugs easy. On the AC side, the IC connector is labeled L for line and N for neutral. Solder wires to the line and neutral and connect to the line and neutral on the power supply. Finally, solder wires to the ground lug of the IC connector and connect to the power supplies. For the lid to my box, I drilled a bunch of holes above where the fans are inside. This is for cooling of the internal supplies once the lid is installed. Okay, if you want to simplify this project, all we need to do is eliminate the dimming feature and get rid of the pulse width modulation controller. In its place, we'll just have the toggle switch bring the 34 volts DC to the collector resistor on the MOSFET current regulator. Note, to do this, we're increasing the value from 10K to 22K to limit the current the NPN transistor uses. We also added a 47K resistor to ground to keep the gate from floating. Here's what would happen without it. Because the input impedance of a MOSFET is so high that without this pull-down resistor to ground, any stray voltage from, touching a wire to EMI could cause the MOSFET to start to conduct. And if the MOSFET starts to conduct, the LEDs will turn on. This resistor prevents that.
Okay, I really hope you enjoyed this Instructable. The things that I want to do to take this to the next level are a little bit of diffusion. If you look behind me, you can probably see some of the color fringing from the white light and the cool white. These are diffused right now with umbrellas, which gives me a nice soft white light. But I think I'm going to look at using some cloth diffusion like you would for a softbox. These could probably make a nice little compact softbox type of light. Definitely need to work on getting some form of barn doors to control the lighting, but these are really bright, and also the MOSFET controller lends itself to a couple other projects. First of all is driving one of those 100 watt LEDs, so now I've got my power supply of 34 volts, the MOSFET controller piece figured out. The potential here is pretty limitless for some really cool lighting. I've ordered some RGB LEDs and a couple 100 watt warm white and cool white chips, so stay tuned because I'll be doing some more video lighting shortly. Have a great day, and I really hope you like this Instructable.